Welcome back, everybody. This is part 2 of the L'Hopital rule notes. So you can see the 3 examples that we worked on last time. So we're going to keep working through the examples that we have here. So we'll move on to number 4, which is this tangent h minus h over h cubed, the limit of that function as h goes to 0. So we can start by just checking with direct substitution. So it looks like tangent of 0 minus 0 over 0 cubed is going to give us 0 over 0. So we can apply L'Hopital's rule. So that's going to equal the limit as h goes to 0 of the derivative of tangent is secant squared minus 1 all over h cubed. And from there, we can kind of see if we want to mess around with the secant and rewrite it in different forms. So we could rewrite it as 1 over cosine squared, or we can leave it as it is. So you can take a moment if you want to work on it, see if you can simplify it in some ways, or we can just set it equal to 0 and see if we get an answer. So if I set it equal to 0, I'll get 0, secant of 0, sorry, which is 1. So secant of 0 squared is just going to be 1 as well. So we'll get 1 minus 1 over 0, which is still 0 over 0. So we can apply L'Hopital again. So we'll get the limit as h goes to 0. Now we're going to have to differentiate secant squared. So we'll use the chain rule. So we'll have 2 secant h times the derivative of secant, which is secant times tangent. The minus 1 will just become 0, and then that'll be all over. Oh, should go back here for a moment. Realize I made a mistake on our first application here. I forgot to differentiate the h cubed, so that should be 3h squared. So then for my second application of L'Hopital, I should get 6h here in the denominator. And we'll get some nice cancellation of 2 at least. So the 2 and the 6 will divide out and become 1/3. But everything else is still going to be there, so if we plug in h equals 0, we're still going to get 0 over 0, because tangent of h is going to give us the 0 in the numerator. So we would need to apply L'Hopital again. So there might be examples like this where you need to apply L'Hopital more than once. So we've got secant squared times tangent. So we're going to need to apply the chain rule and the product rule. So we'll take the derivative of secant squared first, I guess, so which we have here from the previous step. So we're going to get 2 secant h times secant h tan h, all times tangent, plus, and now the derivative of tangent is secant squared, so secant squared and secant squared gives us secant to the 4th h. So kind of a long expression, but we'll see here in a moment that it's going to simplify quite nicely. And we're going to get over 3. So now if we apply h equals 0, that first term is just going to become 0. Right? So that whole thing zeroes out. Secant to the 4th will just be 1, so our answer is going to be 1/3. So 1/3 is the limit of tangent h minus h over h cubed as h goes to 0. So a little bit messier. We had to apply L'Hopital 3 times, but it will still work for us, and this is an example where there's no algebraic method of evaluating this limit otherwise. Okay, so we'll move on to example number 5. So this is going to be an infinite limit. So we've got x approaching infinity, and we've got natural log of x over the cube root of x. So if we do direct substitution, we'll get infinity over infinity, which is an indeterminate form. So then we can use L'Hopital. So then our limit is going to be equal to the limit as x goes to infinity of the derivatives. So we'll have 1 over x, and then the cube root of x is going to be 1 over 3 x to the 2/3. I'm going to write this without rational exponents, so I could have written this as 1/3 times x to the negative 2/3, but actually writing this in the fractional form is going to be more useful for the limit, and this will be true in a lot of cases. So this is going to equal the limit as x goes to infinity if I multiply by the reciprocal of 3 x to the 2/3 over x, which, scoot down here, is going to be the limit as x goes to infinity of 3 over x to the 1/3, which is clearly going to equal 0. And what this is really saying is that if we were comparing our two functions, natural log of x and the cube root of x, the rate at which the natural log approaches infinity is slower than the rate at which the cube root approaches infinity. So that cube root of x is going to approach infinity faster, therefore it's going to shrink to 0, much like if this were x plus 1 over x squared plus 1. That x squared is going to approach infinity faster, so the limit would be 0. So these first 5 examples that we've covered here, these are going to be your typical L'Hopital direct application type of examples. Number 4 is kind of a longer version of that where we have to apply it a few times. But there are some more challenging examples where we have to manipulate our limits first before we can apply L'Hopital. And these ones are going to be a little bit more open-ended. So let's go ahead and drop down to those. So we're going to get indeterminate products is one of the examples that we're going to get. So if we have 0 times infinity, we could also have infinity, well, our most common one's going to be 0 times infinity. So the question will be is, do we approach 0 faster or do we approach infinity faster? Right? So one of those values is going to dominate over the other. So our answers will typically be either 0 or infinity. So if we look at the first example, we'll need to make a slight change to the notes there. I think I put x approaching infinity for the original example, which would just be infinity. But we're actually going to approach 0 from the right. So if we approach 0 from the right, we're going to get x is approaching 0. Let me zoom in a bit here. And the natural log is approaching infinity. Right? So we get an indeterminate product. Now the indeterminate product doesn't mean we can apply L'Hopital. What it does mean, though, is that we can use a bit of algebra to rewrite this. So we can rewrite this limit in one of two ways. We can reciprocate the natural log or reciprocate the x. So I'm going to choose to reciprocate x because that'll make our expression a little bit nicer, as we'll see. So x times natural log of x is the same as natural log of x times 1 over x. So I'm not applying L'Hopital yet, but I am trying to get it into a form that will give me an indeterminate form. So if I do direct substitution now, I'm going to get negative infinity. So we'll be approaching negative infinity over 1 over 0 from the right, which will be positive infinity. And now we can apply L'Hopital. So we're going to have this additional step of manipulating our expression so that we can see L'Hopitals will apply. So if we apply L'Hopital, then we get the limit as x goes to 0 from the right of 1 over x over negative 1 over x squared which is going to equal the limit as x goes to 0 from the right, if we multiply it by the reciprocal, negative x, which is simply going to equal 0. So in this case, that x value is going to approach 0 faster than the natural log is going to approach negative infinity. So our answer is 0. So for the two examples below, 6 and 7, I'll let you do those two on your own. You can check the notes online and see where you get from there. Okay, and so we're going to stop the video here, and then next time we're going to look at some other indeterminate forms. So these last 5 examples